Welcome to Science to Sleep By, and welcome to tonight's quiet journey across the cosmic landscape, where science becomes a gentle lullaby, and the universe unfolds, not with urgency, but with calm, drifting wonder. As you settle in, letting the noise of the day fall behind you, we'll explore a strange and powerful presence hidden deep in the universe, something astronomers once stumbled upon almost by accident. A mysterious gravitational pull, guiding entire galaxies toward one region of space. A silent force with no sound, no light, and no visible shape. They call it the Great Attractor. Tonight, we'll move slowly through the science, carefully, peacefully, like floating through space itself. Everything is explained simply, softly, so you can enjoy the wonder without the weight. Whether you're listening from the warm comfort of your bed somewhere across the United States, or simply taking a quiet break from the world, this talk is made to soothe, to calm, and to guide your thoughts gently into the universe. Now let's begin our journey into the hidden force pulling on all of us, without us ever feeling it, in the quiet vastness of the universe, far beyond the rush of daily life and the familiar comfort of Earth. There exists a gentle motion that carries everything we know. It is not a motion we can feel with our bodies or detect with our senses. It is not a wind pushing against our atmosphere or a tide lifting the surface of our oceans. Instead, it is a deep, cosmic drifting, a slow and steady journey that even our entire Milky Way galaxy participates in. Scientists call this movement a peculiar motion, not because it is strange in a troubling way, but because it is motion separate from the general expansion of the universe. Instead of simply being carried outward by the growth of space itself, our galaxy, along with many others, is drifting toward a particular region of the cosmos. This drift forms part of what astronomers refer to as the cosmic flow, a gentle yet persistent attraction, pulling us across millions of light years. To understand this peculiar motion, imagine the entire universe as a calm lake. On this lake, galaxies behave like tiny boats floating on its surface. Most boats drift outward as the lake slowly expands, creating more room and pushing everything away from everything else. But then, among this outward drift, some boats begin to move in a different direction, pulled towards something beneath the surface that they cannot see. They may not understand what draws them inward, but the pull is real. This is similar to what astronomers noticed when they measured the movement of galaxies near the Milky Way. Instead of drifting only with the expansion of space, many galaxies seem to be moving toward a specific point, a point hidden behind the bright band of stars in our own Milky Way. This motion was smooth and persistent, like a soft current beneath the cosmic lake. The discovery of this motion was not sudden. It was the result of decades of observations, measurements, and quiet curiosity. Astronomers studying the cosmic microwave background, the faint glow left behind from the early universe, observed something unexpected. This glow is supposed to look almost the same in every direction, but it didn't. The light was slightly warmer in one direction and cooler in the opposite one. This subtle difference revealed that our entire galaxy is moving at hundreds of kilometers per second toward a region of space we cannot directly see. That motion told scientists that something massive must be pulling us, even if the source remains hidden from regular telescopes. It was like sensing a gravitational tide tugging at us. Even though the shore creating it was buried beneath fog, this mysterious pull became known as the Great Attractor. Though at the time of its discovery, the name was more of a placeholder for an unknown gravitational region. The name suggested something powerful and enormous, yet quiet and unseen. It did not shine like a star or glow like a nebula. It was not sending out light or sound or heat. Instead, its presence was revealed only through the motion of galaxies responding to it, just as driftwood floating on water reveals the presence of a current. The Great Attractor seemed to exert a gentle but significant pull over an immense region of space, influencing not just the Milky Way, but many other galaxies alongside us. As astronomers continued to study this strange motion, they realized that our galaxy is not alone in its journey. Hundreds of thousands of galaxies, stretching across a region hundreds of millions of light years across, all appear to be flowing toward the same general direction. This collective motion is not chaotic or sudden. It is a smooth, coordinated drift, as though the universe itself has a slow heartbeat guiding entire cosmic structures. Even though the light from distant galaxies takes millions of years to reach us, the motions remain consistent, painting a picture of a universe shaped by invisible hands. One of the most intriguing aspects of this phenomenon is that the region we are drifting toward lies behind a dense area of the Milky Way known as the zone of avoidance. This region is filled with stars, dust, and gas that block our view, making it extremely difficult for Earth-based telescopes to see through it. Because of this natural obstruction, the source of the pole remained hidden for years, adding a quiet sense of mystery to its influence. It was not a mystery defined by fear, but one defined by curiosity and patience. The cosmos often keeps its secrets tucked behind veils of dust and light, waiting for humanity to develop new tools to peer through them. This hidden region reminded scientists that the universe still holds many unseen wonders, many of which can only be revealed slowly, gently, over time. As astronomers observed more galaxies and improved their instruments, the reality of the cosmic flow became clearer. Galaxies were not moving randomly. They were being pulled toward an enormous gravitational basin, a region with far more mass than the galaxies drifting into it. This realization gave the Great Attractor a new role, not as a single object, but as part of a larger structure shaping the flow of galaxies. The actual mass distribution was vast and spread out, but the effect was unmistakable. It was as though the universe itself had carved a valley in the cosmic landscape, and galaxies were rolling gently toward the bottom of that valley. The calm mystery of this cosmic flow gives us a glimpse into the delicate balance of the universe. Even in its grandest scales, where distances stretch across unimaginable space, the movement remains smooth and steady. Nothing about the pole is violent or sudden. Instead, everything drifts slowly, silently, peacefully, across cosmic time, reminding us that the universe does not rush. It simply moves with quiet intention, carrying galaxies like ours along pathways carved by gravity, shaped by matter, both seen and unseen, inviting us to look deeper into its hidden currents and timeless motions. When astronomers first began to suspect that something extraordinary was influencing the motion of our galaxy, they found themselves facing a strange challenge. The force they were measuring was unmistakably real, yet the source remained invisible. It was not hidden in the sense of being small or distant, but hidden behind the dense glow of our own Milky Way. This made the investigation feel almost like exploring a quiet room with a curtain across the window. You can sense the warmth of sunlight behind the curtain, but no matter how you look, the light never reveals the full picture. That quiet uncertainty was exactly what astronomers encountered when they began uncovering the existence of the Great Attractor. The path to this discovery began with careful measurements of galactic motion, particularly through studies of the cosmic microwave background, the faint afterglow left behind from the early universe. This glow acts almost like a cosmic mirror reflecting not light, but motion. Scientists noticed that this glow seemed to shift slightly depending on the direction they observed it, from warmer in one direction, cooler in the opposite. This effect is known as a dipole anisotropy, and it indicated that the entire Milky Way was moving toward a specific region in the sky at remarkable speed. The numbers were not small. The data suggested a drift of hundreds of kilometers per second, a speed far too high to be explained by local gravitational influences alone. This raised an immediate question. If our galaxy was moving so quickly toward something, then what exactly was it moving toward? In a universe full of galaxies, clusters, and vast cosmic structures, it might seem easy to simply point telescopes in the direction we were drifting and find the culprit. But the universe had placed a natural obstacle in the way, an obstacle astronomers call the zone of avoidance. This zone lies along the dense plane of our Milky Way, where thick clouds of gas, swarms of stars, and layers of interstellar dust block our view of the galaxies behind them. When you look up at the night sky and see the wide band of the Milky Way stretching across the darkness, you are looking directly into this zone. Its brightness and density create a beautiful view for the naked eye, but a frustrating challenge for astronomers searching for faint, distant objects. Everything behind that glowing band becomes difficult to detect. Visible light is absorbed or scattered by dust, hiding entire galaxies from view. For decades, this made the task of identifying whatever lay behind that region nearly impossible. It wasn't that astronomers believed the Great Attractor was small. In fact, they suspected it had to be enormous. But without direct visual data, it felt as though they were navigating the cosmos by feel alone, relying entirely on motion and gravitational signatures. It was a discovery not made by light, but by the absence of light, and by the subtle movements of galaxies responding to a gravitational force hidden from sight. To overcome this limitation, scientists turned to tools that could see through dust in ways ordinary optical telescopes could not. Infrared telescopes allowed them to peer through some of the obscuring material, detecting the heat signatures of galaxies that were otherwise hidden. X-ray observatories revealed clusters of galaxies glowing softly with hot gas, giving astronomers clues about regions of high mass concentration. Radio telescopes detected emissions from neutral hydrogen gas, a common component of galaxies, providing further insight into structures lying behind the Milky Way's curtain. Slowly, piece by piece, a picture began forming of what might be influencing the motion of our galaxy. What they found was not a single bright object or a compact core of mass. Instead, they began uncovering sprawling galaxy clusters and dense cosmic structures gathered in the same region toward which we were drifting. These clusters alone could not fully account for the gravitational pull, but they suggested that the Great Attractor was not a singular entity. It was likely a region of space with an unusually large concentration of mass, spread across a broad area and amplified by the presence of dark matter, which cannot be seen but exerts gravitational influence. The more scientists observed, the more they recognized that they were looking at a complex, gravitational landscape rather than one isolated structure. The discovery was made even more challenging. Because the Great Attractor is not just hidden behind dust, it is also relatively close to us in cosmic terms. That closeness makes its influence strong, but its position difficult to pinpoint. Distant objects are easier to map because they appear in clearer patterns across the sky, but something near us exerts influence from many angles, making it harder to isolate visually. It was as though astronomers were feeling the gentle pull of a tide without being able to see the moon causing it. They had to rely on the behavior of the water around them, the motion of galaxies, to infer what lay behind the obscured region. As techniques advanced, astronomers also began mapping galaxy velocities using large all-sky surveys. These surveys tracked the flow of galaxies on immense scales, revealing patterns in their movement. Many galaxies appeared to be streaming toward the same region in space, creating what scientists now call a cosmic flow. This flow was smooth and directional, supporting the idea that a giant gravitational basin was tugging on galaxies across hundreds of millions of light years. Yet even with this information, the Great Attractor remained visually elusive, a reminder of how much of the universe exists beyond the limits of human sight. The deeper astronomers explored, the clearer it became that discovering the Great Attractor would require patience and a shift in approach. Instead of waiting for a single, glowing object to appear, they had to interpret the universe in terms of motion, mass distribution, and subtle gravitational signatures. The process was almost meditative, relying on gentle patterns rather than direct observation. The Great Attractor revealed itself not through brightness or shape, but through the steady drift of countless galaxies responding to its pull. In this way, astronomers learned that the universe often shares its secrets quietly, inviting us to listen more than to look, to follow gentle clues rather than dramatic signals, and to appreciate the beauty of discoveries made not through sight, but through the delicate influence of gravity, guiding entire galaxies across the cosmos in the quiet expanse of the universe, where galaxies drift like softly glowing lanterns scattered across a dark sea. There exists a region whose influence is felt long before it is ever seen. This region, known as the Great Attractor, is not a single object shining brightly or a dramatic cosmic phenomenon bursting with energy. Instead, it is a vast gravitational basin, A gravity well so large and so deep that entire clusters of galaxies, including our own Milky Way, are gently sliding toward it. What makes this even more intriguing is that for much of our history, observing the cosmos, we could not actually see the source of this pull. It lies in a part of the sky heavily obscured by the dense structure of our own galaxy. Dust clouds, star fields, and thick interstellar matter block our view, leaving us unable to look directly at the region where this gravitational force originates. Yet even with that obstacle, the evidence of its presence is unmistakable, because the universe responds to gravity with quiet obedience, and galaxies across vast distances all drift toward the same hidden place. To understand what a gravity well is in this context, imagine space not as emptiness, but as a smooth, flexible sheet. Every object with mass presses into this sheet, creating a dent. The larger the mass, the deeper the dent. Planets fall into the dents created by stars, and stars fall into the dents created by the mass of galaxies. Now imagine something so massive that it doesn't just create a dent, but a wide, sloping valley stretching across millions of light years. That valley is the Great Attractor. It is not pulling galaxies with a sudden jerk or forceful grip. Instead, it creates a gentle downward slope in the fabric of space, causing galaxies to drift toward it the same way a marble rolls slowly toward the deepest part of a shallow bowl. But what creates such a deep gravitational valley? When astronomers first realized how great the pull must be, they expected it to be caused by some enormous cluster of galaxies, something bright and visible that could easily be detected. However, because the region sits behind the dense plane of our own Milky Way, it wasn't visible through traditional telescopes. Over time, with improved infrared, X-ray, and radio observations, scientists discovered that the Great Attractor is not a single cluster, but a massive concentration of galaxy clusters, groups of galaxies, and regions rich in dark matter. These structures together form a gravitational complex, so immense that it influences the motion of galaxies far beyond its immediate surroundings. One of the largest contributors to this gravitational pull is the Norma cluster, an enormous cluster of galaxies located in the same region as the Great Attractor. The Norma cluster contains thousands of galaxies packed tightly together, along with vast amounts of dark matter, exotic, invisible mass that emits no light but accounts for most of the gravity in the universe. Dark matter does not glow or reflect anything, so even when it forms massive structures, it remains unseen. Its presence can be detected only by the gravitational effects it creates, bending light from distant galaxies and directing cosmic flows. The Great Attractor, therefore, not simply a cluster of bright galaxies. It is also a reservoir of dark matter on a scale almost unimaginable, woven into the framework of cosmic structure. Alongside the Norma cluster, astronomers have detected other formations that contribute to the gravity in this region. Filaments of galaxies stretch across space like cosmic highways, feeding mass into the gravitational basin. Hot gas detected through X-ray telescopes fills the space between galaxies, adding to the total mass. Galaxy groups cluster together in knots and webs, forming part of a larger supercluster structure, even though each individual component may not be overwhelmingly large on its own. Together, they build a gravitational landscape capable of influencing the motion of galaxies hundreds of millions of light years away. What makes the Great Attractor even more fascinating is that its mass is spread over an enormous area. It is not concentrated into one bright, dominating point like a star or black hole. Instead, its influence emerges from a wide region, much like how a valley spans a landscape, rather than appearing as a single hole. This is why the Great Attractor eluded detection for so long. It does not shine brightly, and its mass is spread out rather than packed into a single glowing structure. Its very nature makes it quiet, subtle, and difficult to observe, even though its influence is vast. Another key element that shapes this gravitational region is the surrounding cosmic architecture. And although it is completely silent and utterly unfelt, it gives us profound insight into where we truly exist within the vastness of the Milky Way. To understand this drift, Imagine the Milky Way not as a flat disk, but as a vast, dynamic structure filled with stars, gas clouds, dark matter, and swirling gravitational interactions. The Sun does not move along a single, perfectly defined trail. Instead, it follows a path shaped by countless influences, some gentle, some powerful, some ancient, and some continuously evolving. It is like traveling through an ocean with invisible currents, each one subtly adjusting the course of your ship. Over time, these shifts create a delicate pattern of motion, one that carries the solar system through regions of varying density, temperature, composition, and cosmic history. One of the most important elements of this drift is the solar system's slow, wave-like motion through the galactic disk. The Milky Way's disk has thickness, structure, and a vertical profile, not just a two-dimensional plane. As the Sun orbits the galactic center, it also moves up and down relative to the midplane of the galaxy. This vertical oscillation takes millions of years to complete. At times, the solar system sits slightly above the galactic plane. At other times, it drifts below it. During each oscillation, the environment around the solar system subtly changes. The density of stars shifts. The concentration of interstellar dust varies. The influence of passing gas clouds becomes stronger or weaker. These changes are extremely gradual, far too slow for humans to notice. But over millions of years, they shape the cosmic environment through which Earth travels. Another component of the galactic drift involves the solar system's movement relative to nearby stars. Our Sun is not locked in place among its neighbors. Stars in the Milky Way orbit at slightly different speeds, influenced by their mass, distance from the galactic center, and the gravitational tug of surrounding matter. As a result, the Sun gently weaves through local star populations, sometimes moving closer to one group of stars, sometimes drifting away toward another. Over tens of thousands of years, the positions of nearby stars shift in a slow celestial dance. To ancient humans, the stars appeared fixed and eternal, but in truth, they are all moving, all dancing across the galaxy with us. This drift also means that the solar system is slowly traveling toward a point in the sky known as the solar apex, located near the bright star Vega in the constellation Lyra. This motion is incredibly subtle, about 12 miles per second relative to nearby stars, but over long periods of time, it changes the orientation of the night sky. It means that the sky of the far future will be filled with constellations unfamiliar to us, shaped by our movement toward new stellar neighborhoods. Among the most mysterious influences on this drift is dark matter. Although invisible and undetectable by conventional means, dark matter forms an enormous halo around the Milky Way, extending far beyond the visible galaxy. This halo contributes the majority of the galaxy's mass, and its gravitational pull guides the paths of stars, including the Sun. We do not feel it, we do not see it, and yet it shapes the very course of our cosmic journey. It determines how the Sun sways through the galaxy. It influences our orbital velocity. It defines our position within the gravitational landscape of the Milky Way. In many ways, the drift of the solar system is a conversation between the Sun and the galaxy's unseen mass, a gravitational whisper exchanged across millions of years. The galactic drift also affects the cosmic environment Earth passes through. As the solar system travels, it encounters interstellar clouds, vast regions of dust and gas left behind by ancient stars. These clouds can vary dramatically in density. When the solar system passes through a denser region, it can subtly distort the heliosphere, the protective bubble formed by the Sun's solar wind. A compressed heliosphere may allow more cosmic rays to reach Earth, influencing atmospheric chemistry or interacting with cloud formation. These effects are far too tiny to notice in everyday life, but they remind us that Earth's environment is not entirely isolated. It is influenced by the galaxy's architecture, by the cosmic weather of interstellar space, and by the slow drift of the solar system through regions shaped by ancient explosions, dying stars, and the remnants of galactic evolution. Even the night sky reveals the story of this drift. As Earth drifts through the galaxy, the alignment of the stars changes slowly over time. In tens of millions of years, familiar constellations like Orion and Ursa Major will no longer exist in their current form. Stars will shift, patterns will dissolve, and new patterns will slowly emerge. The night sky is a cosmic map, always changing, always evolving, always reflecting our movement through the Milky Way. The stars we see today are a snapshot of our current position in the galaxy, a position that humanity has occupied for only a fleeting moment in cosmic time. This drift also reminds us that we are part of a galaxy filled with structure. Spiral arms, dense clusters, thin regions, thick regions, and even regions filled with the energetic remains of supernova all shape the environment around us. The solar system is currently located in a small interstellar neighborhood known as the local interstellar cloud, which itself is moving through a larger cavity called the local bubble. These structures were carved by ancient stellar explosions, long before the sun existed. They are the fingerprints of the galaxy's past, and the solar system drifts through them like a traveler wandering through landscapes shaped by forgotten histories. Perhaps the most poetic aspect of this galactic drift is the way it reframes our sense of home. We often imagine Earth as stationary, the sun as central, and the galaxy as a distant and changing background. But the drift reveals that nothing is fixed. Home is not a single point in space. It is a path. It is a journey. It is a movement through an ever-changing cosmic environment, carried by forces vast and ancient, guided by gravity, dust, stars, and the invisible framework of dark matter. Earth is not just orbiting the sun. It is drifting across a galaxy that is itself moving through the universe. And in this drift, in this gentle passage through cosmic space, we find our true place, not fixed, not still, but part of an elegant, continuous journey through the Milky Way. When we imagine our place in the universe, we often think of Earth moving around the sun, or the sun guiding the planets around the Milky Way. But the story of motion does not end with our solar system's orbit. There is a deeper layer, one that stretches across unimaginable distances and unfolds across billions of years. This is the motion of the Milky Way itself, a giant spiral galaxy drifting, falling, and flowing through the cosmic landscape. And as the Milky Way moves, everything inside it moves as well. Every star, every planet, every dust cloud, and every living thing on Earth is part of that motion. It is a quiet journey, one we do not see or feel, but one that shapes our place in the cosmos. To understand how the Milky Way moves, imagine a city floating on a vast, invisible ocean. The galaxy is like that city, drifting through a sea of cosmic structures, pulled and nudged by gravitational currents we can barely measure. Our galaxy is not anchored to anything. There is no fixed point in space where the Milky Way rests or spins. Instead, it is carried along by the gravitational pull of massive clusters, superclusters, and even larger arrangements of galaxies that form the cosmic web. The Milky Way moves at astonishing speeds, around 1.3 million miles per hour, toward a region of space called the Great Attractor, a mysterious gravitational anomaly buried within the Laniakea supercluster. Even though the name sounds dramatic, the motion is not chaotic. It is slow, steady, and incredibly smooth, stretching across millions of years. The Great Attractor is not a single object, but rather a gravitational focal point created by the combined mass of millions of galaxies. Our galaxy, along with many others in our region of the universe, is gently falling toward this region. It is not a fall we will ever feel. The pull is so subtle across such vast distances that every part of the Milky Way moves together, perfectly synchronized, as if the galaxy were a single, unified body. And because everything inside the galaxy is bound by gravity, we move right along with it, unaware that we are part of a grand cosmic migration. But the Milky Way's motion is not driven only by this attraction. The galaxy also drifts through space as part of the local group, a small collection of galaxies that includes Andromeda, Triangulum, and dozens of smaller dwarf galaxies. The local group itself moves through the larger Laniakea supercluster, which spans 520 million light-years. Imagine the Milky Way as a small boat caught in the current of a giant, slow-moving river. The river stretches so far that we can only map small portions of it, and the current flows so gently that the entire boat moves uniformly. We move with the local group, not because of a single force, but because gravity creates enormous pathways across space. And galaxies follow those pathways like leaves drifting on a breeze. Our galaxy also moves because of dark matter, the invisible substance that makes up most of the Milky Way's mass. Dark matter creates a giant halo round the galaxy, shaping its motion and acting like a gravitational cushion that holds stars in place. Without dark matter, the stars in the Milky Way would spin too fast and drift away. But with it, the galaxy remains stable as it travels through space. We do not see dark matter, but we feel its influence. It forms the gravitational skeleton that guides the galaxy's motion and connects it to other galaxies across the cosmic web. Just as the bones of your body support you without drawing attention to themselves, dark matter supports the galaxy in silence. Another layer of motion comes from the expansion of the universe itself. Space is stretching in every direction, causing galaxies far from us to move away at increasing speeds. However, galaxies within gravitationally bound structures like our local group or the Laniakea supercluster do not drift apart. Their internal gravity is strong enough to hold them together despite the expansion. This means the Milky Way is caught between two forces: the inward pull of gravity from nearby clusters and the outward push of cosmic expansion. These forces balance in a way that creates a gentle, continuous drift across billions of years. We are not moving in a straight line or toward a single destination. Instead, we are flowing through space along a path shaped by gravity, mass, and time. Even the Andromeda galaxy plays a role in the Milky Way's motion. Andromeda and the Milky Way are on a slow-motion collision course, expected to meet in about 4.5 billion years. The two galaxies move toward each other at around 250,000 miles per hour. But again, this motion is so smooth and so slow on human timescales that it does not disturb our daily lives. The galaxies are far too large, and the stars far too spread out, for any dramatic effects to occur anytime soon. Instead, this motion adds another layer of calm inevitability to the galaxy's journey. We are part of a cosmic choreography that takes place over eons altogether. The Milky Way's motion is a quiet reminder that everything in the universe is in motion. There is no stillness in the cosmos, only layers of movement that unfold across distances too vast to fully comprehend. Yet even though we travel through space at unimaginable speeds, we feel none of it. Gravity holds everything together, keeping Earth stable and life calm as the galaxy glides through the universe. The motion of the Milky Way is gentle, coordinated, and perfectly suited for life to unfold on a small blue planet drifting silently through the stars. When we ask how fast Earth is moving, the answer isn't simple, because Earth is never moving in just one way. Our planet travels through the universe on several levels at once, with each layer of motion stacked on top of another like a series of gentle, invisible currents. We are not just rotating, just orbiting, just circling the galaxy. We are drifting, falling, gliding, and flowing through cosmic space in a complex pattern of motion that seems overwhelming when described, but feels perfectly calm from where we sit. This layered motion defines our cosmic existence, and yet, we live our entire lives without feeling even a fraction of it. First layer of motion is Earth's rotation. As Earth spins on its axis, every point on the surface traces a circular path through space. At the equator, this path moves at around 1,000 miles per hour, though the speed slows as you move toward the poles. This spinning creates day and night, sets the rhythm of our lives, and acts as the foundation of the motion we are most familiar with. But compared to the greater motions of the universe, Earth's rotation is only the beginning. It is the smallest wave in an ocean of cosmic movement. The next layer is Earth's orbit around the Sun, at around 67,000 miles per hour. This motion is much faster than Earth's rotation, though we still do not feel it. The orbit is smooth and stable, held in place by the Sun's gravity. Gravity creates a kind of cosmic tension, a balance between Earth's forward momentum and the Sun's pull inward. This balance ensures that instead of flying off into space or falling into the sun, Earth moves in a long, gentle loop around our star. The journey takes a full year to complete and lays the foundation for our seasons, the tilt of our planet, adding the variation that shapes the experience of summer and winter. Even though this motion is fast, it feels effortless because the entire Earth moves as one unified body. A third layer of motion comes from the movement of our solar system around the Milky Way. The Sun, along with all its planets, sweeps through the galaxy at around 514,000 miles per hour. This, too, is a journey we never sense, because the solar system moves together within the Sun's gravitational field. We orbit the galactic center roughly every 230 million years, a cycle sometimes referred to as a galactic year. During one galactic year, entire species evolve and vanish, continents drift, oceans rise and fall, and civilizations rise and disappear, all while the Earth quietly follows the Sun on this vast celestial loop. Even this tremendous speed means little when measured across the enormous scale of the galaxy. But it adds another layer to the question of how fast we are truly moving by, and the solar orbit is another layer, the drift of the entire galaxy through space. The Milky Way itself moves at around 1.3 million miles per hour as it falls toward a region known as the Great Attractor. This enormous gravitational region, made up of galaxy clusters and dense structures, exerts a subtle pull across millions of light years. The Milky Way is not alone in this motion. It travels in the company of many other galaxies, each one following a similar path through the cosmic web. This motion adds a fourth layer to our cosmic speed, even though we never experience any sensation of movement. Studying this region has taught scientists patience and creativity, encouraging them to look beyond traditional wavelengths and to use computational reconstruction to fill in missing regions of cosmic maps. The Great Attractor became one of the first major discoveries pulled from this visual silence, a reminder that our observational horizon is not the boundary of what exists, but merely the boundary of what we have learned to perceive. As surveys grow more sensitive and telescopes more powerful, the zone of avoidance slowly shrinks in mystery, yet it continues to remind scientists that the universe still holds secrets behind every shadow, waiting with patient gravity for us to find them as we reach the final moments of this quiet journey through one of the universe's deepest mysteries. The Great Attractor stands before us, not as a singular discovery, but as a reminder of how vast, intricate, and delicately connected our cosmic surroundings truly are. From the gentle drift of our Milky Way to the sweeping motions of entire clusters and superclusters, the universe reveals a choreography so smooth and expansive that it almost feels like a lullaby written in gravitational language. We followed the subtle flow of galaxies, traced the hidden pathways inside the zone of avoidance, and watched the Great Attractor emerge from behind the veils of dust and starlight, not as a monster or anomaly, but as a natural part of the cosmic web, a gravitational gulf quietly influencing the motion of everything around it. This journey has invited us to view the universe not in terms of chaos or fear, but with a sense of calm, wonder, and perspective. We discovered that large-scale cosmic motion is not rushed or violent, but gentle in its enormity, unfolding over hundreds of millions of years. We learned that the Great Attractor is not a threat, but a waypoint within an even larger structure, one piece of the Laniakea supercluster that we call home. And we saw how the limits of our perspective, like the zone of avoidance, do not diminish the universe's grandeur, but instead challenge us to look deeper, adapt, and uncover what lies behind the light we cannot see. In this soft and reflective space, we are reminded that even the greatest mysteries of the cosmos do not demand urgency. They invite patience. They whisper rather than shout. They allow us to drift through ideas the way galaxies drift through space, carried by gravity's gentle pull. And in that drifting, we find comfort in the scale of it all, comfort in knowing that the universe is vast, ancient, steady, and beautifully interconnected. As this exploration of the Great Attractor comes to a close, we rest with the understanding that the universe is still unfolding its secrets, slowly and quietly, and that our place within it is small yet meaningful. Our galaxy moves with millions of others in a cosmic dance older than memory. And tonight, in this peaceful journey through science, designed to ease the mind, we have simply floated along with it, letting the vastness of space cradle us in its serene, unhurried rhythm.